Okay, so when's your exam? Thursday. Who's invited? My people. I will be here most likely by 8. I might even be here earlier. So you can start it at that point. I do have to leave. Actually, a very hard time when I have to leave. I do have to leave by 4, just because of something going on that I have to do. Other than that, I handed out a. You have the review sheet. I already gave it to you. I handed out a new one, and all I did was remove one thing from it. The stuff on metals, insulators, and semiconductors we did last on Friday. I'm removing that and I'm putting it on the next test. The other thing is we will not be having a class on Friday. Okay, so there will be no class on. Okay, so I want to kind of go back over these ideas we had before. So I want to talk about a simple view on band theory. I guess. Okay, so let's talk about a free particle. So we said for a free particle. Okay. What did we say the energy and the wave function was for? So how do we find this? Good review of the on Thursday. So on Thursday, I could easily say find the energy and the eigenfunction, the eigenvalue, and the eigenfunction for a free particle. And you would always say easy peasy, because what would you do? I want you to show me all the work for that. What would you do?
Write the energy.
Okay.
E equals
E equals
1/2 mv squared plus
1/2 mv squared. V squared. Okay, I'll make this V. Now I'm going to take a free particle. So what am I going to do with the V?
V 0.
Yeah, I'm going to set it to 0 because it's going to be free. Okay. So I can put plus 0 here. Okay, now what?
Now you write it in terms of the operator.
Okay, so we have to do something first.
M over N.
Remember, when you have this, you can't have any V's in here, the velocities. It has to be written in terms of position and momentum. So what do we do with this? We write this as M over M. So that gives us this P squared. I'll put a little X here over 2M E. Then what?
Then you write it in terms of the operator.
Okay, so this goes to
IH bar pressure with respect to T.
okay, and this X on your saw here. And this goes to
E minus IH bar
so
squared.
this goes to PX acting on PX, which is
Minus IH bar squared. Partial is or partial squared with respect to X.
yeah, so this guy here is this. So PX acts on PX, what do you get?
X squared.
I agree.
92 px squared.
Minus H bar squared. You saw over this to them. Then a derivative acting on a derivative is a second derivative. Here. Now we did our separation of variable part. Now I'm gonna kind of skip some steps here. We did this. We wrote this as what?
Psi X equal.
Now it's a function just of position and a function just in time. We put this in here. I'm going to skip some steps, and what happened? Our equation split. So the equation split into 2 pieces here, giving us this IH bar, portion T is respect to T, for T, and this is our energy, and then into this guy over here. And is this still on the board? It is. Okay. What's the distinction between this one and this one?
The first one was time independent.
And that's time independent, this is the time dependent. So that homework, the homework 5, what are you gonna be, and they give you that step thing like that? Which equation will we be solving?
Time independent.
The time independent one. Okay. So what do we do with this? What's the next step of this?
We're gonna fix your MH bar over.
And we'll take all the stuff over here. And we've seen that before, and what do we do with that?
That's k squared.
That is by definition our k squared. It's always k squared when
B is 0.
more general.
B is less than E.
Yeah, when your e is greater than v. Okay, it is beta squared when
E is less.
v is greater than e. Okay, so we have that. Then when we solve this here, what does it give us? It gives us this p equals plus or minus ik. And so we could write this in truths. I could write this as psi 1 equals e to the ikx. And psi 2 equals e to the minus ikx. What do those represent?
Traveling right to the right and left.
Now, how do I know this one's going to the right?
Because the IKX is positive.
Oh, prove it to me. Suppose you go to the store and you want to buy a traveling wave to the right, and the clerk brings you this wave function. Okay, and you don't recognize it. What would you do to the wave function to see if you have the right one?
Do you look at it at infinity?
Yeah,
Or like as it approaches infinity, what does it do?
yeah.
have 2
I have to go to 0.
That's going to oscillate. So this even at infinity, it oscillates. What happens if px acts on this guy here? Remember, this is minus IH bar, r with respect to x, e to the IKX.
You get positive H bar K.
Yeah, so if you take the derivative, that pulls down an IK. So this gives you H bar K. And that gives you this. So what kind of problem is this?
Eigenvalue, eigenfunction.
Eigenvalue, eigenfunction, right? This is my eigenfunction. This is my eigenvalue. As we're dealing with momentum, this is my eigenvalue, and it is positive, therefore it is going to the right. This is positive. I'm traveling to the right. Because it's linear momentum. If it's negative, then the linear momentum would be to the left. That makes sense? So that's what we have here. Now, if we plot this energy here, all right, since we have this, since we have k squared, who's this guy, we get our energy for free. We make a plot of this. We get this E versus K. And this is what we have. Okay, now, what is this over here? Tell me about these values and tell me about these values over here.
The right is the positive IKX.
Okay, so that means these are waves going to the
right.
This is waves to the right. These then are the waves to the left. That makes sense. Now, yes,
Can you just explain that graph again real quick? Sorry.
this is quadratic. So this is just like y equals x, which is quadratic. So I'm plotting this equation here versus k.
Okay.
So it's just quadratic. That makes sense? Now, let's put on periodic boundary conditions on this. So, how can we impose? Or let's actually. So suppose we wrap the x-axis on itself. Okay, what does that mean? So here's my x-axis. That's all fine. Imagine this is a wire like this. Now imagine I bring the two pieces together like this. So I'm going to take it and to make this my x-axis. Okay. So my distance along this would be my x. Anywhere along here would be x. I'm going to say the whole distance around here. I'm going to call L. Okay. Now, what's the boundary condition then on my wave function?
L.
It has to be
Yeah.
continuous over x.
Oh. So I'm going to draw this here. So here's my x. This is x. And what would this distance right here be?
L.
That'd be L. So if I have my psi x here, what would I have to have here? Psi x plus L. What would have to be the boundary condition then?
Psi x has to equal psi x plus L.
Exactly.
In the partial.
So you'd have to have this. Okay. Let's find out what that means. So this is e to the ikx. This is e to the ik x plus L. What kind of crazy thing happened?
Oh.
This is e to the ikx. This is e to the ikx. E to the ikl.
You can cancel the ik axis.
They cancel.
Then use the ik axis. Take the natural one. That's
Yeah.
L.
When is e to the ikl equal to 1? Oh, sure, but then we don't have a wire, right?
Nice.
But then we don't have any. we don't
Oh,
have
is
a
it-
function.
is it the integer rule?
If you tell me what that means, I might.
Yeah.
And it's like
Okay, what do you know about e to the I anything? It equals
sin.
be specific. Got this before? You had
Cosine KL plus sin.
this to have to be cosine of KL plus I sine KL. Okay, is there any imaginary term here? No. We have to kill this term. And then your cosine of KL has to be then 1. Okay, so KL, what value of KL would give me a cosine of 1 and a sine of 0? There. There, okay, but then I get a trivial solution.
Or k
2 pi,
over L
2 pi,
and over L.
2 pi n, where n's an integer, right? So this meaning is that your KL here would have to equal some n. Okay. So your K, I'm sorry, 2 pi n. Okay. So your K here is 2 pi n over L. That makes sense? So if this L is large, this K is basically, you can, you're gonna have a whole bunch of different values of K here. That makes sense? Okay. Now you're still gonna have the same energy diagram here like this. You're gonna have this E here like this. I'm gonna have my K here like this. Now this I'm gonna have basically, I'm gonna have a whole bunch of little, I have discrete values here like this. So this would be n equals 1. This would be n equals 2. This would be n equals 3. I have an infinite number of values like this. And the same over here. This is my n equals minus 1, n equals minus 2, so on and so forth. I'm still more or less going to get something that still is going to be my. Not that at all. Let's see. I'm still going to get my overall graph like that. Okay. Is that all fine? Now let's take our little system here, and I'm going to put on a periodic potential. Imagine now. And take the same problem. So now impose a periodic potential on the on this problem. In other words, here's my problem here like this. And you're gonna have something here, then 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 something here. And you call this distance here A. So this is A. Every single distance A, I'm gonna have a dot. Or I'm gonna have, it doesn't matter what it is, I'm gonna have something. This is gonna be my periodic potential. Okay, so the question is, what would that mean? It means the following. Periodic potential means V of X equals V of, it's truly periodic. If the distances, they're all A.
Which would be V of X plus A.
It has to be a V of X plus A. So maybe if I graph this out, I'm just going to give you an example. If I plot V versus X, to be something that looks like maybe this. Doesn't have to be this. This is just a simple example. But this is A. Right. But you have the same thing over here. Okay. That'd be an example of periodic potential. Now what's going to happen here? Well, here's my energy. What did we say happens when we have these things? So if I have a particle coming this way, what did we say happens?
Some part will reflect and transmit.
Yeah, you get these reflected and transmitted parts. Okay, so what's going to happen here? What that means here, I'll draw one over here. Okay, it means that here, I have some e to the I kx. Then A plus B e to the minus I kx. That's going to be here, in this region. Okay. Then in this region, I have something else. I have something similar. Over here, I have sort of the less psi, I call this region 1. So we're region 2. The psi over here, I'll call it 2. That would be C e to the I k prime x. This B e to the minus I. Why is it a different K?
Is the potential's different?
Yeah, here the potential is 0. Here the potential is something not 0. So that's why I have different values. Make sense? So we said for certain values of K. Okay. I've stated this and I'm not going to prove it because it turns out it's an involved proof. Eventually I would do the solid state course, take that class, and or take Professor Kirkland's class, and I'll probably show you in that class as well. Something happens. What do we say happens? For certain values of K, you form standing waves. The incident and reflected waves form standing waves. Okay, I'm just saying that as I clapped my hands and said it is thus. I'm not. This is not a proof. I'm just saying it happens. So what's going to happen here is if I were to draw like a little picture of this, I'm going to replace these by basically just a dot here. So I'm going to put my, see, here's my video for this. So when I drew this little thing here like this, and I put these little dots here like this, that's what this is here. Okay. And we said the standing waves are going to be like this if you're to plot these. You're going to get one that looks like this. And again, I've not proved this at all, I'm just saying. So this is one standing. And the other one then is going to be basically in between here. So here's the other. Standing wave. Now, would they have the same energy? No, these do not have the same energy. Which one would be lower in energy than the other one? Yeah, how come? Because this is an electron, right? This is an electron. This is basically peaking over the nucleus or over the atom, which would have a positive charge. So I'm having more negative charge over a positive charge there. The potential energy for that, the electrostatic energy would actually be lower. Over here, well, it's going to be higher compared to this one here. So this one here, solidly, will have a lower energy value. Due to the electron being found more likely over the positive atom. So what that does here is then it basically puts a gap in that energy level diagram. What happens here, we initially have this. This is without a periodic potential. In other words, we don't have this. That doesn't exist. When we put this in here, instead of having this, we now have something that looks like that. That's not very symmetric, does it? Okay. And then this would continue to go up like this. Okay. What happens here is that for this value here, I put like a star on it. And so for these values, standing waves occur at this value. Okay. So this is the one here. This is the one with the lower energy. The standing wave with low energy. And this is right, this one here, that one here. This is the setting of the larger energy. Okay. What do you have in between here? Is there any energy levels in here? No, there's no energy levels in there, and that's a gap. That's why it's called a band gap, because there's no energies there, levels here. So when you hit this region here, there are no energy levels in the gap. So this is called a band gap. These are bands, this is the gap. The region is called the band. How to redraw that without all the dotted lines and stuff, then get something that looks like this. Yep.
Do each one of those levels correspond to a standing wave with a higher energy level?
Yep. So this is going to correspond to another K value. You have another one.
Oh, gotcha.
You can actually work this out very precise, but not at this. Okay. So does that part make sense? Now, let's fill these, and this is where we're going to get different things. So I can put the energy levels in here. So if I draw the energy levels, I'm just going to arbitrarily draw something. These are the energy levels in these regions here like this. So let's actually start filling these. So let's say I put electrons in here, but this is only partially filled. So let's partially fill the lower level. So I'm going to draw that. I have all these here, these levels here. So I basically have electrons here like this. For technical reasons, you can have, it turns out you can have more than just these two electrons I'm having here. It turns out you can have a lot more, but I don't get there. That's partially filled. So what does that mean here? That means we have a certain number of particles going to the left, a certain number of particles going to the right, an equal number of particles going to the right, left. That make sense? Now, if I put an electric field on it like this, so here's an electric field. This is an external electric field. What can happen?
Some of the electrons jump towards the
Yeah, the electron's going to be, there's going to be a force on them this way. These electrons here cannot go over here. Now, what happens about the number of electrons going to the right compared to the number of electrons going to the left?
more electrons to the right.
Yeah, more going to the right than to the left, so there is going to be a net current going to the right. Does that make sense? In this case here, there are more. Moving to the right. So this conducts electricity. Material conducts. So the material conducts current, we call it a metal. So this is the metal.
Is it kind of similar to the energy level problem where it takes a certain amount of energy to shift the electrons over, or do they just jump freely?
So when you actually go through and work it out, the spacings here. I'm drawing a big gap here, they're almost insignificant.
Oh,
This is almost continuous. There. So it takes actually very little to move them up. Okay, but it does take an external fill like this. That's gonna supply the work that you need. Now I've worked out the details on that, and there's some things out there. Okay. Now, if you have this case here. So. Let's completely. On the lower level. And. Assume. The large. Band gap. Here's a lower level, here's all my levels. Like that. And assume that this is large. And now I'm going to fill it. Okay, now if I put an electric field here like this. And these go over here. No, because these are all filled. Okay, so what happens? What do you know about the number of particles going to the right compared to the number of particles going to the left?
And they're the same.
They're the same. And we can't move any of these over here. We could move them up here if basically if you put in a strong enough electric field, that would destroy the device. But you get them up here, okay? So they're not going to be able to go up here because this gap is too big here. So the number of particles going to the right equals the number of particles going to the left. There's no net current. So we call this a
Insulator.
this is an insulator. Okay. Now, let's have the same problem, but what are we going to do to the gap?
Make it small.
Make it a lot smaller. So repeat with a smaller gap. This. Okay. Because that's just going to represent all fill. So I'm talking drawing we're seeing that. They're going to have a small gap. Now an electric field like this. Now what can happen?
Put the particles to the left and jump over to the right.
Yeah, this is going to be small enough. There's going to be thermal energy just in the room and the device. And what can happen here is you can take some of these and actually move them up to here. Not as many as you could in the other case where, you know, when this band was partially filled. Okay, but you can get some here. So you can get partial conduction. So there's going to be slightly more electrons moving to the right. Okay, so it conducts, but not the greatest, okay, but it does conduct. So you call this a semiconductor. This is a C. Okay. And if it's pure, you call it what? In other words, we don't, it's all silicon, it's all germanium. So it's all pure, we haven't put crap in it yet. You can call it just a pure semiconductor. Often sometimes it's just referred to as like intrinsic as well. Intrinsic silicon. It means you haven't put crap in it. Okay. Now, the novel parts of these occur when you put crap in them. Okay, what do you call when you put in crap? You call it doping. And so when you put in extra stuff in here, what it does is it introduces energy levels basically in between here. And so when other atoms are added to pure semiconductors, it is bumped over. Okay. And what it's going to do is going to introduce additional energy levels between these gaps. These additional atoms introduce new energy levels in the cat. So let's draw this. Okay, I'm going to put a slightly bigger gap in here just so we can kind of see what's going to go on. Grab this. Now these all filled. They're going to get these new levels in here like this. This is your E. So this is basically, this is from the atoms. From the additional atoms. And what do you know about those additional atoms? What can they do? There are two types.
Oh, and if you think
Positive or negative.
There are N and P types. Okay, so let's we'll have these all filled up here like this. So these atoms are two varieties, N and P. Once we learn a little bit more, I'll explain how an NP junction works, but we need one more piece of physics. So these types of atoms, these additional atoms are called N and P impurity. N and P impurities. Dopants. What?
Dopants.
Dopants. Yeah. Dopants. Okay. So let's do the end one's a little bit easier to see. Look at that. Yeah, I'm really tired of drawing this picture. And you probably are too.
It needs a stamp.
It does need a stamp.
I just copy pasted Dr. Wise. I feel bad for you.
So here we can okay, everything's filled. So if you have N type, what do they do? Why is it called N? It stands for negative. Well, these are going to be, this is going to have basically additional electrons in these states here like this. Now these additional electrons here, basically they're closer to this bottom gap here. So this is going to be a lot easier for these to hop up than these ones down here. Okay? That makes sense? So you can have these extra electrons and they can go into here like this. So it's basically these are going to supply extra electrons. So the N type supply extra electrons. Okay. The P type, what's going to happen here is they're not going to supply, they're going to have instead of what it's called a hole. So if you have a P type, I can have an electron here, then basically I can have a vacancy here, a vacancy. Meaning it doesn't have an extra electron here. But since it has a vacancy there, what can happen? It's going to be a lot easier for one of these fellows here to pop up into there. Okay, like that. And they're going to be the P types. Okay.
So would adding the P types take more energy to pop them up to the next energy level because they have to fill that hole?
Well, I mean, you can still deduct them from here just fine. I
Oh,
mean, that's going to conduct here, but then you can also then go from here over there as well.
Okay.
And that's just after, once you get one going over here, then you can take one from here and fill it up there.
Mhm.
And get things going.
Is I tallied out my. What I think that today.
I tallied it out too and got 0. So I added 12 and 0 plus 12 is 12. Are there any questions on this? Okay. So you can see what we can do is just with this simple idea here, we can actually get a good understanding of what it means to be an insulator, what it means to be a metal, and what it means to be just with these simple ideas. Again, with a little more quantum mechanics, you can actually make this really, really rigorous. See exactly what it is. Okay. Take the course in quantum mechanics in the spring, and we'll work out the periodic potential. I'll show you a lot more detail with this. Okay, questions? Okay. Our problems have all been one-dimensional. What do we need to do?
2 and 3.
2 and 3-dimensional. Okay, I'm gonna do the 3-dimensional case, and hey, let's look at some crazy. It looks like there's a daily homework 2, curriculum code 9. Okay, let's actually do next Wednesday, because basically we're not having class on Friday. I wanted to I'll probably be finishing it up on Tuesday. You're gonna be doing the 2-dimensional case. Okay, I'm gonna do the 3-dimensional case for you now. So we want to talk about quantum mechanics in 3 dimensions. So how do you do quantum mechanics in 3 dimensions? You can't. It's too hard. Okay, next topic. Okay, so if something seems too hard in life, it probably is. So go on to something easier. Look how far I got. So that's just what do we do? 3 dimensions. Okay, so how do we do it? You're pros at this. Where do you start?
Classical energy.
Yes, E equals kinetic plus potential. Hey, what's kinetic?
1/2 mv squared.
1/2 mv squared. Hey, now what?
And do m over n.
All plus top and bottom here with the mass. Hey, now what? Before we party, okay, we're gonna party. What do we know about p squared in 3 dimensions?
Oh, x, y, and z.
Yeah, p squared is really the p vector, not in the p vector. Where is the p vector?
Px, x hat plus py hat.
Pxi hat plus pyj hat plus pzk hat. So what is p dot p?
Px squared plus py squared plus pz squared.
Yeah. X squared plus py squared plus pz squared. Now what do we do? Now we party. Because that potential could be a function of x, y, and z. Hey, now what?
And you get a IH bar partial with respect to d.
Yeah, so this goes to our IH bar, partial with respect to t.
Is it just h bar squared times the gradient over 2n?
Yeah, this is px acting on px, so this guy goes to
Oh, IH or minus IH.
this guy, right? So this guy again is going to be our px hat, and px hat. And this fellow here is going to be the py hat, and py hat. And this guy here, pz hat, and pz hat. What are they all going to give?
Minus squared.
Okay, you can get a minus h bar squared over 2m, just minus h bar squared, here's my 2 over 2m. Then this guy goes to the second derivative for x. Then likewise, for the next one, you can do the same thing with the y, and then the same thing with the z. Yeah. And then what do you know about x hat, y hat, and z hat? They are
X, Y,
x, y, and z. Okay, can I pull out a minus h bar over 2m on that? And I'm left with this. This is given a name. What is that called?
I'm just kind of
Del.
That part there, that is the Laplacian. Okay. This is by definition that symbol. This is called the Laplacian. Okay. Then this acts on a wave function. So we're going to get this. So this is, give me the whole name for it.
It's independent.
Undependent, three-dimensional, non-relativistic. Schrodinger. This is when I just want to start saying random things, just so they can actually figure out what we're saying, and then it's good. That's just. Again, I inherited my father's very inappropriate sense of humor. Any questions about that? Okay, so. Hey, let's do a special case. Let's assume that V is
Zero.
not that special.
Infinite.
A constant. Let's solve this for a constant V. Okay, what are we gonna do when you go to the hydrogen atom? That V is gonna become what? What would V be for the hydrogen atom?
Is it? It's the question.
You all had physics 126.
Oh, isn't just a cool.
So it is what?
K.
K
D squared.
Q1, which would be, you know, your ZE times
Q2.
Q2, which is your minus E over
R squared.
over R. Okay. And then if you put that in there and then solve it, that's what your hydrogen atom. What are going to be the eigenfunctions? Your SP and DF orbitals. That's what they are. So when you solve that, basically it's going to be a time independent piece. That's going to be your SPDF orbitals. So when you have those SPDF orbitals, all they are is the eigenfunction for your hydrogen atom. And those energy levels, the minus 13.6 over n squared, they're your eigenvectors. Okay. Okay, so let's solve this. Well, that'll be the next topic. We're not going to do that right away. And just so you know, when we get to that part, it's going to be very, we're going to be skipping a lot of steps. And the reason why we're skipping a lot of steps, well, if you take my final course in the spring, you'll see why. Then I won't skip the steps, and it's going to take 2 weeks with you doing a lot of daily homework to basically get the entire thing. I won't skip any of the steps, and here's an edge. But you'll see where I'll mention. All will be reviewed. So let's look. Let's solve is equal to with B equal to constant. Okay. So I clap my hand and B is a constant. Our psi here is a function of x, y, z, t. From there, you tell me exactly what to do next.
You can separate it into psi of x, y, and z, and then psi of t.
That's what we're gonna do. We're gonna write this as a function, just a normal psi of x, y, and z. And then some capital T like this. And what's that called?
Separation of variables.
That's separation of variables. Where does that go?
Into psi there.
It goes back into our original equation. So if I take this psi here and put it back into, what can I pull out on the left?
The psi x, y, z.
I can pull out this part here because this is not dependent on t. So I can write this as IH psi partial t with respect to t equals. I wrote this part here. I'm going to rewrite this as h psi. What is my h called again?
Permission.
It is remission, but it's called the
Hamiltonian.
that's your Hamiltonian. Okay. Now this Hamiltonian only depends on position here. And so when I put in my psi here, what can I pull out? I can pull out the capital T. You tell me what to do now. Your pros of this.
Divide both sides by t.
So you divide it by the original solution again. And you always do that with these. There's no variation of these. You tell me what happens next.
You said the left side equal to e.
Well, you skip some steps. That's all true. But go through the argument.
We still have t on that show.
Oh, thank you.
Oh, take it, yeah. They're
Go through the argument.
independent and
There's an important piece of the argument that's just in terms of words now.
they're independent variables.
Yeah, so this only depends on t. And this only depends on x, y, and z. Okay, what do you know about x, y, and z, and what do you know about t?
All independent.
These are independent variables. So t and x, y, and z are independent variables. Therefore,
They have to equal constant.
yeah, because of this here, both sides must be a constant. So therefore, both sides must be a constant. Okay. So I can put in any value of little t here, any random value of x, y, and z and t. They're always the same. The only way that can be the case is that they both equal constant. Okay. And what do we take that constant to be?
E.
The energy E. We're going to take this to be E.
Is there an argument for that just being e or
I was just going to ask you, why did we do that? Has to do with this. What is your Hamiltonian?
the
Kinetic energy operator plus your
potential?
potential energy operator. And your kinetic energy operator plus your potential energy operator would be the total energy of the system. So the eigenvalue would then have to be then the energy of the system.
Oh, yeah.
Now, what is this equation called?
I can.
It is an eigenfunction, eigenvalue problem. Good. What else is it? Big, long, fancy name.
Time independent.
the time, three-dimensional, time-independent, non-relativistic Schrodinger equation. This one here, if you put in all the bells and whistles. In here. This is your time. Independent. Three-dimensional. Non-relativist. Schrodinger equation. Does that make sense? Hey, tell me how to solve it.
Move the V over.
And one more thing.
Oh, and the 2n H bar.
Yeah, it's gonna be the exact same thing. We're gonna take our V over here and multiply by my little buddy here. There's only some good name to call that. K squared. Okay, so you're gonna define this to be. K squared, is that marker still showing up? Getting weak. It is still showing up. Okay. You tell me how to solve that now. I'll write it here.
Zoom in general.
So it's this guy. You saw here the function of x, y, and z. If there's only something we could do,
Could you split it up into psi x, psi y, and psi z?
I'm gonna write it as basically a product of three functions. One function that only depends on x, one function that only depends on y, and one function that only depends on z. I'm gonna make these script. So I'm gonna have basically, I can call it chi. So I'm gonna have some big function chi, only a function of x, some fancy function y, only a function of y, and some fancy function z, only a function of z. If only I could do something with that term. What do we do?
Plug it in and then divide by the original.
And that's the same form of all these. So this right here goes into here. So if I put this in here, what comes out on this side?
You can pull out the psi y's.
The y and the
And the z.
z. So this becomes fancy y, fancy z. Here. Next one becomes
That would be x and z.
the x and the z. And the next one,
So
the x and y. Now, if there's only one more thing I could do.
px.
Not yet. Yep.
Why are we assuming that the v is less than? Like it's always k. We always
Yeah, the
have
k,
k.
whenever you have k, this is here. We're gonna do the case when it's not. We're gonna do the case when it's flipped, and then this will become then everybody bail.
Oh,
But right now
so
we're just assuming.
right, so just
Yeah.
okay.
Now, what's the next step with all these?
divide by the original.
You divide through by the originals. This term here becomes 1 over chi. This becomes this. That becomes this. That becomes this. Okay. You're pros at this. You keep on going on with the argument. What do you know about this? What do you know about this? What do you know about this?
They're all independent of each other.
Oh, yes, but go through in the argument. This can only depend on what? This only depends on X. And this, Y, and then Z. This right here is this is. What do you know about X, Y, and Z?
Oh. Are we talking about independent of each other?
They're independent of each other. So what we have. So your X, Y, and Z are independent variables. Okay, so I can put in any random value of X, any random value of Y, any random value of Z, and they always equal the same constant. What's the only conclusion we can make? So if this has to be a constant, and if this has to be a different constant, and this has to be a different constant, but if I add all those three constants together, it always has to equal minus k squared. So this has to be a constant. Call that Cx. This has to be a constant, I'll call this Cy. This has to be a constant, I'll call this Cz.
Dr. Lux, where did the psi go that was beside the k? What happened to that?
This one here was the chi yz.
Mm-hmm.
We divide by chi yz,
Oh, gotcha.
so they cancel. So what this gives me is it gives me this guy. This one. Next. You add these all together. Where Cx, Cy, Cz equals minus k squared. Does that make sense? Okay, so why is this called separation of variables? What have we ultimately ended up doing? We separated the variables, so it's really, really well named. And this is why this technique is used everywhere. That's why I say when you look at the four most important math techniques in all physics, this is one of them. Okay. This is a sledgehammer. Okay. Now we're going to go to a specific type of potential, which is going to be what? We're going to go to the infinite well. So what do you think is going to happen in the infinite well? What do you think happened?
K squared goes to 0.
Yeah, yeah. So let's put this over here.
Oh,
So let's solve this problem. For infinite, so the infinite well is going to be, if this is x, y, z, We call this here A. We call this here B, and we call this here C. On the interior of the well, what do you think the potential is going to be?
Sure.
And take it to be 0. If I'm on outside here, what do you think the potential is going to be?
Infinity.
It's going to be infinity. Okay. So basically, the particle's only going to be able to stand on the interior. So what do you think is going to be the boundary condition? When your wave function's at the side of this box, that wave function is going to have to be
0.
It's going to have to be 0. Can't go out. It's stuck in the box. So, for the infinite well, the wave function here equals 0 on the sides. Okay. So what would they be? That'd be that's the psi and 0y here equals 0. And so this is so if I were to say shade that in, where is that in this picture here?
Side there. Is it the front face of the
Yeah, this would be
back face?
the back side. This would be the front side. What would be the right and left?
The y equals 0 and y equals b.
Yeah. So this is this right here. This is front and back. Okay. We're going to do this one. This is right. Left sides. What's top and bottom?
Z equals 0 and c.
This would be top and bottom. Okay. I'm just going to state what we're going to get, and then we're going to prove it on next Tuesday. Again, we have no class on Monday. I'm sorry. We have a class on Monday. We have no classes going Friday. Okay. We're going to prove. So we will prove. We will prove next Tuesday that the energy eigenvalues are going to depend on 3 quantum numbers, x, and y, and z. So you get 3 brand new quantum numbers. This is going to be minus h bar squared pi squared over 2m. We get nx over a squared plus ny over b squared plus nz over c squared. We're going to get brand new physics in this. Okay. Going to get novel physics with that problem, and a very important lesson in life. Okay, enjoy your day. And no class on Friday.